Good afternoon, everyone. For those of you who do not know me, my name is Mark Edwards. I'm a senior science advisor with the Office of the Chief Scientist and your host for today's seminar. On behalf of the entire OCS team, welcome to our science seminar series and to today's science seminar. First, I'd like to mention, as you may have noticed from the notification, that we are recording today's seminar. If you would like to ask questions or have comments at any time, you are welcome to put them in the chat. Now, the chat will not be recorded on the video, so you can submit your questions here, there anytime. Recordings from previous seminars, as well as this one, will be provided on the Alberta Environment and Protected Areas YouTube page, and new recordings will be posted there in the near future. It's my honor today to do the land acknowledgement. I want to respectfully acknowledge that our Edmonton offices are located on the traditional lands and gathering place for Treaty 6 nations and the diverse Indigenous peoples, including the Cree, Blackfoot, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, and Anishinaabe, and the Métis and Inuit peoples, and many others whose histories, languages, and cultures continue to influence our vibrant communities today. In keeping with the tradition of gathering, these science seminars provide an opportunity for us to get together, to exchange knowledge on the very interesting science going on in Alberta within an open learning and sharing environment. The hope being that through our dialogue today, we are all able to improve our awareness and understanding and can move that along to support evidence-informed decision-making wherever that occurs. To help maintain the call quality today, your video and audio have been disabled, and we encourage you to enter any questions or comments you have at any time during or after the presentation via the Teams chat function. I will read out the questions and comments in the order that they were received at the end of the presentation. So today we welcome Dr. Greg Courtice. Greg is a water resource engineer who specializes in river engineering, ecohydraulics, aquatic habitat compensation, and the management of suspended sediment in low-tech environments. He has spent the last 5 years undertaking doctoral studies at the University of British Columbia, Okanagan campus to develop a framework for the management of temporary suspended sediment releases derived from river construction projects. Greg completed his master's degree at the University of Alberta in 2014, where he investigated nature-like fish passes in Arctic headwater systems. As part of this work, he received the Canadian Society of Civil Engineers Donald Stanley Award for Best Paper in Environmental Engineering. Greg's consulting experience includes playing a key role in responding to the 2013 Southern Alberta floods through his work planning, designing, and overseeing construction of over 40 flood mitigation structures and habitat compensation measures. So, over to you, Greg.
Thanks, Mark. I'd just like to say thanks for the opportunity to speak today. I'm going to be going through some of the research that I undertook as part of my doctoral studies, and I recently defended this. Yeah, my research topic was on managing temporary suspended sediment releases to improve environmental and economic outcomes for river construction. So first, I just want to provide a brief overview of what this is all about. So, for example, the city of Calgary here that you can see in this image, it's bisected by the Bow River, and often you have communities that like to develop around rivers because it provides a convenient source of fresh water among other amenities, and this convenience can come at a cost when flood events can damage infrastructure, and they can also create other public health and safety risks. So as a river engineer, I design solutions to this problem where we try and minimize the risk of flood events having impacts to communities. What you see here is a recent image of a construction project that I worked with the city of Calgary on to remove a large gravel berm that was under the Center Street Bridge. And the reason for doing this was that there was this sort of blocked the conveyance under the bridge. So we attempted to increase the flow capacity during flood events. And one of the challenges that we have with these projects is that we release suspended sediment into the river. And this can be harmful to aquatic ecosystems under certain exposures. And as you see in this video, even the act of having construction equipment in the river for very brief periods of time when necessary can result in or will result in suspended sediment releases. So these releases are in a lot of cases unavoidable and we want to attempt to minimize the harm that they have the potential to occur. So we have this interesting concept that results from trying to manage these releases. So we have a fixed scope of work that has to be done to accomplish what needs to be done to protect the infrastructure or improve the health and safety, public health and safety around rivers. And so that scope can't really change. We can change other scopes of work around that to try and mitigate some of the environmental risks, but the fundamental work that needs to be done in a certain way. So this leads to a management trade-off where we can either get the project done quick with a intense sediment concentration, or we can get the project done slower with a less intense release. And current practices generally prioritize reducing concentration, and that's sort of implemented through a limit to the amount of concentration that can be released at any given time. And generally what's prescribed is based on the Canadian Council of Ministers of the Environment guidelines for the water quality guidelines for the protection of aquatic life. And they cite 25 milligrams per liter over 24 hours as an acceptable risk tolerance threshold. Now, in practice, these short-term exposures generally apply a hard limit of 25 milligrams per liter, which forces us into this longer duration, lower concentration scenario for a suspended sediment release. From a economic or engineering perspective, we look at this and say, okay, well, a longer duration is likely going to result in a higher cost because of equipment time and labor time. And on the ecological side of things, we aren't really sure which one of these is better because we have concentration and duration both playing a role. And so the ecological risk is uncertain. So those familiar with suspended sediment effects on fish may be asking, okay, well, how does the Newcomen-Jensen severity-ville effect scale play into this? This is a study, a meta-analysis that looked at all of the available dose response observations that were either published or sufficiently detailed non-published observations. And what they did was they categorized these observations from 0 to 14 in increasing severity and then fit this to a multiple linear regression model. And this work was critical in describing how duration and concentration are both important for explaining the dose response relationship for fish in when exposed to suspended sediment. From a ecological risk assessment point of view, this can be a bit challenging to interpret the uncertainty associated with the risk because the multiple linear regression model has a normally distributed error term that's applied over the entire range of exposures, and that coincides to all different levels of responses. Now, the measurements and modeling, or the measurements and methods used to describe behavioral effects or document behavioral effects are likely going to be different than the lethal and physiological effects. So when we apply that error term over the whole range, there's a bit of ambiguity with how do we interpret this for a formal risk assessment. So what this tells us is there's likely a better approach to statistically modeling and quantifying the risk associated with suspended sediment exposures on fish. So what I did was I digitized the data set in Newcomb and Jensen and updated it with new observations. So there's 25 years since this study was published. So I took all of the salmonid observations and I added these additional published studies to this data set, and I recategorized this into a more coarse effect categorization that corresponded to similar methods to document the observations, as well as it corresponding to similar consequences. So all behavioral effects have a sort of similar consequence, while major physiological and lethal effects obviously have a very severe consequence. And then we have this middle category of minor physiological effects that is in an intermediate category. And so once this was digitized and categorized, I plotted these observations to see if we can detect some sort of trends in this data. And so the main panel you see here is just a standard bivariate scatter plot where we have concentration versus duration, and the points are plotted as a shape and color to represent the different categories. So circles are behavioral, triangles are minor physiological, and diamonds are major physiological and lethal. And moving out from the main plot, we have rug plots that are these sort of dashes that you see above, just on the border of the main plot, and they present the data by life stage, and they're color coded to those response categories. And then beyond those, we have univariate scatter plots that correspond to their respective axis. So the one on the top is ranking observation by exposure duration and categorized by the response category, and then the same thing on the right side of the plot for concentration. And one thing to note here is that if we're trying to find trends in each variable individually, we can look at those univariate scatter plots to see if we can pick anything out. And for the most part, there aren't any discernible trends here. If you look on the right side in the concentration univariate scatter plot, all three categories are sort of overlapping over most of the range of concentration. So alone, we don't see a whole lot of a trend develop. Now, if we take the product of concentration and duration and plot something similar, we get a much more discernible trend here. All the behavioral observations, for the most part, are towards the left, lower exposure doses, and at the right, we have more major physiological and lethal observations. So this is ranked by suspended sediment dose, which is the product of concentration and duration. And this is in a natural log transformation. So I've also created a more precise categorization to see if we can discern any more precise trend using categorizations that are similar to the Newcomb and Jensen severity of ill effects scale. And what we see here is that there isn't much of an improvement to this trend detection with those more precise categories. So that suggests that our more coarse categorization is more appropriate for the data we have available. And again, there's a rug plot on the top of this to separate out the trends by life stage. And here we don't see much of a trend between adult and juvenile. There may be some more severe responses a little bit lower on the dose range, but overall they're fairly similar. So now we want to look at okay, how can we quantify this statistically? And one of the things that was considered is that this minor physiological category is a bit ambiguous. And one of the reasons why it's ambiguous is because these effects such as heightened blood glucose or long-term survivability issues and sublethal stress, they're all things that you have to really be looking for them, or they have to occur over a sufficiently long duration. And so some of these effects could be occurring in the behavioral observations, they just weren't looked for. So what we did was we removed this minor physiological category to make a very defined interpretation of how we want to statistically analyze the data. And so what was chosen was a logistic regression framework where we used a multi-level or mixed effects logistic regression to be able to understand if a study effect may be present. So whether or not there's different variability in the sensitivity to suspended sediment by each study. And so what we did with this framework is that we looked at how well we could classify the observations and how well this type of model would fit if we use different predictors. So this logistic regression model basically estimates a probability of major physiological and lethal effects given this predictor. And the equation that I've got on presented there is a bit of a simplification because I don't represent this multi-level component to it. However, for those familiar with multi-level modeling, the study effect that we were modeling with this was retained in the intercept, that alpha term. So I won't get into any more of the details of the modeling because I don't have time, but essentially when we used AIC to evaluate the model fit for the relative for the model construct. So we evaluated different predictors, for example, dose on its own, the natural log of dose on its own, dose with life stage, the natural log of concentration, and the natural log of duration. And so what we found with this AIC value, what we're looking for is a very low value. If the value is high, that means the model doesn't fit the data as well as a low value. So the natural log of dose on its own, with considering a study effect, found that we got the best fit for the model. And then on the other side of the modeling, what we look for is specifically how well the model will classify observations between behavioral effects and major physiological and lethal effects. And what we found is that also that dose alone with the study effect, it produced a very good classification performance. Not quite as good as dose with life stage, but there could be a potential for overfitting with adding another variable into the predictors. And so from there, what we can say is that it's likely that dose is going to be the best predictor for explaining this relationship based on this logistic regression framework. So we can create this conceptual operating space that says, okay, well, if the probability or severity of fish responses is increasing for an increase in dose, which is represented by these contours, these are dose contours in a concentration and duration space, we can overlay our considerations for this management trade-off, where a project gets done either quicker and more intense or slower and less intense. And in addition to that, we can consider that the longer it takes to get the project done, the more costly it's going to be. So this is a very simplistic representation of this management problem. Now, the one uncertainty we have is that it's likely that concentration and duration may not have the exact same effect on this relationship. So to say that both of these management options with this trade-off are exactly the same risk is likely not true. So how do we quantify our prediction uncertainty? So to do that, what I did was I took this initial logistic regression model and I separated out dose, the predictor of the natural log of dose, into individual predictors for concentration and duration. And then I also added on an interaction term to be able to evaluate whether or not a high or low concentration is going to have a different effect for a given duration. And so the three of these predictor terms allow us to inform a better quantification of prediction uncertainty. So that's a bit complicated and abstract to look at the statistical equations, but what does this look like in practice? So here is a plot that represents our prediction uncertainty. And so the benchmark limit that I show here corresponds to those CCME guidelines of 25 milligrams per liter over 24 hours. And we want to know what locations have a similar probability, estimated probability to this benchmark limit. And so how I derive this uncertainty space, which I'll describe a little bit more as I show you the process that went into this. We have through this modeling and fitting the data to the model, we have a correlated set of parameter estimate distributions. So one for the intercept, one for the concentration parameter, one for the duration parameter, and one for the interaction term. And so these are correlated. So what that means is that we can pick a value of, say, the intercept. We can randomly draw a value in that intercept distribution, and that'll correspond to specific values in the other distributions. And so with this set of parameters estimated, we can estimate a probability for that benchmark limit. And given that we now have an estimate for that probability, we can say, okay, well, where else in this exposure operating space has that same probability? And the bolded line is what that corresponds to. That's where the same probability exists in the exposure operating space. So now we can run that a bunch of different times and run a Monte Carlo simulation. And we get different estimates to that probability at the benchmark limit and other places in this exposure space. So we run that a bunch of times, and through this study, I ran 10,000 of those iterations, and the red management band, the uncertainty band, corresponds to 90% of those draws. So there's 5% below and 5% above. We could also say that there's a 95% chance that the exposure space below this band has a lower probability than at the benchmark limit that has already been defined as an acceptable risk tolerance. And now I want to make it very clear that this work doesn't specify where an acceptable or what an acceptable risk tolerance is. It takes an existing risk tolerance and extrapolates over the entire exposure range. So using this information and this result, I created a management operating space for exposures that are realistic to find during construction activities. And this is in linear space. So this management band uncertainty is the same uncertainty band that you saw in the previous figure, only this time it's in linear space. And I've overlaid dose contours on that so we can see how a dose contour may be able to represent this uncertainty. And what we find is that at the benchmark limit, the dose contour that intersects that actually coincides very closely with the lower bound of the management band uncertainty. And so another component of this figure that is important to point out is the benchmark limit below the at the that's sort of bounded by 25 milligrams per liter over the whole duration. That corresponds to sort of the traditional management approach. And so what we can see is that if we're given a exposure, a release that's within that operating space represented by 0.1, if we increase the efficiency of getting that project done, we're likely to increase concentration at as a result of a reduction in duration, and we're gonna bring this exposure into what's still an acceptable range, but outside of that traditional operating space. And we can see that based on the management band uncertainty, we're still providing a environmentally acceptable exposure, given that we've set the threshold, the acceptable exposure threshold at that benchmark limit. So with the understanding that dose provides a reasonable representation of this more complex management band uncertainty at the contour that intersects the benchmark limit, we may be able to set a dose limit instead of a concentration limit and allow ourselves to capitalize on this management trade-off. So how do we actually apply that to the project? So first, you have to select an acceptable dose limit, which we can set 600 milligram hour per liter, corresponding to the CCME guidelines. So again, the actual threshold, risk tolerance threshold, needs to be given, and then we can set a dose limit that corresponds to that. Then we have to record high frequency turbidity measurements to estimate and resolve the time series. So this would be done at a location downstream of the work at a specific location identified as a good representation of this plume. And so from here, we would collect this time series. We can calculate a time-weighted mean concentration using the time series and use this to inform a maximum daily duration by dividing the dose limit by the mean concentration that we've estimated. And this duration limit for the exposure coincides closely with daily construction duration. So we can prescribe the number of hours in the day that a construction activity can occur based on how that mean concentration is corresponding to the dose limit. So dose divided by how what we're seeing from the monitoring as far as a mean concentration goes equals our daily construction duration. So I wanted to provide a bit of a case study on a project that I worked with the city of Calgary on. And what we did here was we created a gravel berm to isolate a portion of the river to be able to undertake construction activities. And we used a operating limit based on both concentration and duration, and we were able to compare using different strategies to see which strategy provide the most economical and environmentally acceptable solution. So here's a summary of of everything that happened. I'll be getting into the details of this more clearly, but what I want to point out in this figure is that you can see the footprint of the berm, and you can see that it took us 3 days. We had April 4th, April 5th, and April 6th. And within each day, we had a different construction approach. So April 4th, we carefully placed the gravel to try and reduce concentration. So it took longer to get work done, but we attempted to reduce that concentration to satisfy a prioritization of concentration. On April 5th and April 6th, we prioritized efficiency. So the way these activities differed between April 4th and April 5th and 6th is that on April 4th, we used an excavator to carefully place the gravel in bucket by bucket. On April 5th and 6th, we dumped gravel right next to the river, and then we slid it in with a bulldozer. And so the summary of day one, we had 650 cubes placed, and that took 4.5 hours. And we had a mean concentration of 36.2 milligrams per liter over 6.75 hours. And that was monitored downstream of the work. So on day 2 and 3, we prioritized efficiency using this bulldozer approach, and we placed about 1,800 cubic meters per day. The day 2 had a duration of 2.5 hours, while day 3 had a duration of 6.5 hours. And the reason that took longer on day 3 is just due to facilitating the work. You can see in this photo that the berm got quite long, and that just took a lot longer to place the gravel. And here's a video of the gravel actually being placed. So you can see it just get slid in the water. So the concentration was higher on day 2 at 67.5 milligrams per liter, and day 3 it was lower due to the fact that it took longer logistically to place that gravel. And so here's the results. So on the left side, we've got this time series of instantaneous concentration measurements, and the horizontal line corresponds to the mean concentrations. On the lower figure, we have a time series of the cumulative gravel placed in each day. And so you can see that there were periods in April 4th, in the first day, that construction was halted to try and get that concentration down. And so between those 3 days, you can see that day 2 and 3 have a much steeper curve here, and that corresponds to higher production rate. Now, what's interesting when we shift to the right plot is that the dose, when we divide the dose value for each day by the gravel volume placed, we get a much higher value on April 4th, corresponding to essentially what that means is that for a volume of gravel being placed, the higher the value is in this parameter, the more fine sediment is getting released into the river. So even though April 4th we attempted to reduce concentration, it resulted in more fine sediment going down for a given volume of gravel. And now these results can be a little bit complicated to compare between days. So I created a graphical summary of this by plotting the mean concentration time series as the dashed line for each day. And above that, I've created a ribbon that corresponds to the time series of gravel placement. So the wider that ribbon is, the more gravel is placed. And so I've also included a dashed dose line that allows us to compare if the exposure is above that line, that means it's a higher risk, and if it's below that line, it's a lower risk. And so you can see that April 4th ended up being a higher dose than the other 2 days, and it placed a much less amount of gravel. So we can say that April 5th and 6th, improving the efficiency of the construction project resulted in both an economic improvement and an environmental improvement for evaluating effects of suspended sediment on salmonids, which is what our model did. So to conclude, we have this concept of a fixed scope of work that results in a trade-off of concentration and duration. Concentration alone is a fairly poor predictor of effects relative to dose, and we can't really characterize the plume without duration of exposure for ecological risk assessment. And we did find that dose does provide a good representation of mean dose response dynamics in salmonids. And this case study sort of demonstrates this in practical terms, that using both concentration and duration can allow us to capitalize on this management trade-off. So here's references that were just cited in the presentation. And I just want to thank the City of Calgary for their efforts to consider my research in some of their projects. And I also want to thank my co-authors. I think a couple of them are on the meeting here, Chris Cahill and Andrew Paul. And their help has been critical in ensuring robust statistical analyses and keeping me in line as far as the ecological components of the work goes. Thank you.
Thank you, Greg, for a really interesting talk and really interesting work. I really appreciated actually the videos that you actually put in there and the imagery, the drone work. I think you must have done for some of this.
Yeah.
Really helps to visualize it. Thanks everyone for joining our science seminar today. Our next science seminar will be on November 22nd, and we'll be hosting Jody Krakowski on White Bark Pine Ecosystem Foundation of Canada, who will be presenting on endangered white bark and liver pine recovery in Alberta. I hope everyone can join us for that. As a reminder, if you're not on our mailing list to receive invites to our science seminars and would like to be added to it, or if your team has work that would like you to share on an upcoming seminar, please contact the Office of the Chief Scientist at aep.ocs.gov.ab.ca. That's it for today. Thanks again, Greg, for sharing your work with us. A really interesting presentation. And to everyone who tuned in, we'll see you next time. Thank you.